I was looking through my old math textbooks to find the best problems, and one of them is finding the odd values in the row of Pascal's triangle. And if you don't want to know what Pascal's triangle is, it's pretty simple. You have a row of ones, and for each cell, you basically add the previous two cells above it to get its value. So for 10, you add 4 plus 6. For 2, you add 1 plus 1. And you can build a whole triangle that goes out to infinity like this. So the question is, given any row of this Pascal's triangle, how many odd values are in this row? For example, in row 5, over here, we have 1, 5, 5, and 1. So there are 4 values. And row 9, we have 1, 9, and then 9, and then 1. That's another 4 values. So pause the video now and see if you can solve this problem, and we'll get into the solution in a bit. Cool. So one thing to notice is that if you actually count out all the values per row, you get this table here. And for the g of n being the odd values in any row. So for n equals 0, we only have one odd value, which is 1. For n equals 3, we have 4 odd values, which is 1, 3, 3, and 1. And we can keep going this way. And you notice that the pattern repeats every time we have a pattern of 2, a power of 2. 2 to the 0, we start at 1. 2 to the 1, we start at 2. And then 2 to the 2, start at 2. 2 to the third, we start at 2. So it's a very kind of recurring pattern, and sort of hints that the powers of 2 are very important in this case. And another interesting fact is that p, for any specific cell, you can calculate the value directly without having to go through this whole triangle, just by calculating n choose k, where n is the row you're in, and k is the value, starting at 0. So for example, 28 is going to be, we're starting in row 8, and this is position 0, then position 1, and then position 2. So 28 is actually just the same as 8 choose 2. And we can calculate that out, saying, 8 choose 2 is going to equal to 8 factorial over 6 factorial, 2 factorial, which is going to be 8 times 7 over 2, which is going to be 56 over 2, or the same thing as 28. Cool. So to work with this problem, there is a theorem we can use. And this theorem states that 1 plus x to the 2 to the k is the same as 1 plus x to the 2 to the k mod 2. The mod 2 is basically going to eliminate all the middle terms in this polynomial. And what's great about this is that it will help us, it will show us exactly how many terms are going to be odd, because only odd terms survive a mod 2 operation. We're eliminating all the even numbers. So to prove this, let's start with the base case. 1 plus x squared. Let's expand this out. 1 plus 2x plus x squared. And we remove the 2x because it's going to be even, because there's a 2 right there. And then it becomes 1 plus x squared mod 2. So that seems to work. We were able to turn 1 plus x squared into 1 plus x squared. Alright, so now let's assume that n equals k equals true. N equals 2 to the k is true. And let's look at n equals 2 to the k plus 1. So in this case, 1 plus x to the 2 to the k plus 1 is the same as 1 plus x to the 2 to the k times 2. And then, you expand this out algebraically, and then we can use the fact that n equals 2 to the k is true, so that means 1 plus x whole to the 2 to the k is equal to 1 plus x to the 2 to the k squared, and then we apply our same expansion algebra again, and this 2 cancels out, and then these 2 to the k's combined, as you can see here, and it becomes 1 plus x to the 2 to the k plus 1 mod 2. And we're done with this proof. So what does this help us do? With this proof, we can then show that for 1 plus x to the n, you can actually decompose it into a binary expansion. So 1 plus x to the 2 to the k to the 1 plus 2 to the k to the 2 plus to 2 to the k to the p. So you can expand this out. Right now this is standard algebra. We're just basically multiplying these terms together because addition and exponentiation converts into product in the terms. And then we can use our theorem. And this is super cool. We can take all these values and then bring the exponent inside in mod 2. And what you can notice is this becomes 1 plus x to the 2 to the k1 all the way to 1 plus x to the 2 to the kp mod 2. And there are p terms of 1 plus x to the 2 to the k. And therefore, because each value is going to be multiplied by each other value, it's basically there's 2 terms here, 2 terms here, 2 terms here in each parentheses. And there are p terms overall. And they're all going to be multiplying with each other. So there's going to be 2 to the p terms when you multiply this all out. And what's cool about this is because these are the only terms that are surviving, therefore in row n, only 2 to the p terms survive, Therefore, only 2 to the p terms are in the row n that are odd in Pascal's triangle. So that's kind of abstract, so let's look at what this means. So 1 plus x cubed is the same as 1 plus x squared times 1 plus x, which is going to equal to 1 plus x squared times 1 plus x mod 2, which is then going to equal to 1 plus x squared plus x cubed. There are 4 terms here, and therefore there are 4 terms for n equals 3 that are odd. And you can see this here. We have 1 plus 3x squared plus 3x plus x cubed. You have 1, 3, 3, 1. And you can see the same thing here in Pascal's triangle. 1, 3, 3, 1. And so there are 4 terms here and 4 terms here, and only odd terms survive, so this formula really gives us a good estimate. And so let's look at another one. Like 1 plus x to the 8th is going to be, with our theorem, 1 plus x to the 8th mod 2, and therefore there are only 2 terms. And we can see that here, and we go to the 8th row, we only see 2 odd values. We just have this 1 here, this even all the way through, and then 1 here again. So what's nice about this formula is that we can take values that are far more difficult than for a computer to calculate. If a computer wanted to calculate 2049 rows of Pascal's triangle, it would take a lot longer than this method, which basically says we decompose it into powers of 2, which is going to be 2048, which is 2 to the 11th, plus 2 to the 0, which is 1, and then that becomes 1 plus x to the 2048 times 1 plus x, which is going to be 1 plus x to the 11th plus times 1 plus x. So therefore, this thing is going to expand out into 4 terms. So we can say with confidence that on row 2049 for Pascal's triangle, we're only going to have 4 odd terms, which honestly is pretty amazing. So basically the general theorem is if you decompose any n into its binary expansion, and you count the number of ones, 2 to that number is going to be how many odd values are in that row. And what's really cool about this, I'll leave you with this, is that if you actually circle, we looked at all the odd values, but if you actually circle all the even values, you're going to get something very interesting. You're going to get 2, and then 4, 6, 4, and then 10, 10, 20, and then look at the next row. There's nothing odd here. There's nothing even here. Let's look at this row. We circle all of these. And then continuing to circle all of this. All of these are even. And do you notice there's like a little pattern here? Well, what's cool is that this is going to look like the Sierpinski's triangle, which is a fractal. So I'm going to leave that as a mystery for you to look up on your own. But thanks for watching the video. Hope you learned something. Bye.